Welcome to our next lecture in the series on condensed matter theory. In the previous videos I have showed you how we can work with continuous fractions to describe your Green's function and how you can think of the Green's function of a large system as the Green's function of a smaller system then that couples to the rest of the system, and you then need to know how you propagate through the rest of the system via the coupling that you have between the small and the larger system. All the examples that we showed you in the previous videos were examples in one dimension. And this method in one dimension is substantially simpler than in any dimension, but the method is generally extendable to also 2 and 3 dimensions. And the method is also related to several other methods that we use and can define in physics. And that's something that I would like to discuss to you in this short video to show you how we can actually generalize the examples that we had. And also in the introduction video on continuous fractions, in principle was general. So what we have seen is that for a one-dimensional system we can look at an Hamiltonian, and the Hamiltonian is given by sides with an on-side energy that can hop to other sides with maybe some other on-side energy. So the Hamiltonian, in terms of matrix representation, is given by a band diagonal matrix. And this matrix represents a one-dimensional model where we have on-side energies epsilon and hopping t. So we have in hopping sum over I, epsilon I, a dagger I, ai, plus a hopping ti between a dagger I plus 1, ai, plus a dagger I, ai plus 1. The Green's function of such a system, well, if you look at the side 0 of 1, 1, R1, R1 is given by 1 over the Green's function of the side where we add the particle minus the coupling to our neighbors. You couple in there with t, you couple out there with t, t square, and then the Green's function of the rest, which is the Green's function of adding or removing a particle to the second side, omega plus I0 plus minus epsilon 2, which we again can do by looking at the Green's function of this side and how it couples to the rest, omega plus I0 plus minus epsilon 3 minus T3 squared, etc. So we immediately get a continuous fraction for the local Green's function starting for an Hamiltonian that is band diagonal, that represents a one-dimensional model. So that's the kind of examples that we had in our lecture and in the examples that we had so far. So what do you do when your system is not one-dimensional, but when your Hamiltonian is maybe even dense? Well, we can always generate an Hamiltonian that represents the same system and is of this form, or represents a one-dimensional chain. So let's say we create and annihilate a particle in state 0. So we look at G 0, 0 of omega. Now we want to generate an Hamiltonian of this form. So we want to look at a new state, which we can call state 1. And we want this state to have a few properties. We want the matrix element of the Hamiltonian between state 0 and state 1 to be equal to T0, and we want that for any other state the Hamiltonian which state 0 is 0 for all states I that are not equal to 1. We can do this, and the claim is that my state 1 is equal to the Hamiltonian times state 0. And we can prove this. If I look at my Hamiltonian matrix element between state 1 and state 0, then this is given by psi 0 h squared psi 0, and this is equal to T0. So in order for T0 to be non-zero, we have to make sure that h psi 0 is not 0. And then we have the overlap between two wave functions, which has to be 0 if we have an orthonormal basis set. So that has to be true for all states psi I not equal to psi 1. That also means that psi I h psi 0, because that is just psi 1, is equal to 0. So indeed, if we define psi 1 equal to h psi 0, then all states orthonormal to psi I have to have 0 Hamiltonian matrix elements with psi 0 itself. So you might now of course wonder what happens with psi 0, because psi 0 is also a state that is not psi 1, and of course psi 0 h psi 0 is not necessarily 0. But now we should realize that our psi 1 is not necessarily orthogonal to psi 0. And it's exactly the overlap between psi 1 and psi 0, which is the energy of psi 0. So for psi 0, this doesn't hold. What we can of course do is, instead of continuing with psi 1, we orthogonalize psi 1 to psi 0, we normalize it as well. And then everything else that we did here is still equally valid. And we indeed find that in this way we get a state to which you couple, and all other states that are orthogonal to those have no coupling. So if we take as a basis for our Hamiltonian the state psi n given by h to the power n times psi 0, then we find that our Hamiltonian is band diagonal and becomes in that respect 1D-like. So you generate a one-dimensional model. You show the path in your crystal through which you hop. Now this basis is known as a Krylov basis. And the method to generate this basis is generally known as the Langchos method. And there are several methods in computer science now that are based on Krylov bases and Langchos methods to diagonalize matrices or to work with, well, Green's functions. response functions of real materials. These two methods and this realization that you can always project your system to a one-dimensional state, and for a one-dimensional state the Green's function of your full system is given as the Green's function of two subsystems that you couple to each other, is also the basis of numerical renormalization. Group theory. And for the later, the aim is basically to derive a low energy effective Hamiltonian where many of the high energy degrees of freedom are projected out, such that you end up with a simpler system with less degrees of freedom that still contains all the essential physics. It's basically the idea to look at the single band around your Fermi energy and taking all the occupied and unoccupied bands out. But now for more general Hamiltonians, where you are even allowed to put in interactions between the electrons directly. So when you later in your study come either to some numerical methods where you use this or renormalization group theory methods, then you might very well find that several of the notations and formulas that we use and the handling of Green's functions that you use will come back in those methods. For now, thank you very much. This was all that I wanted to say about how we can deal with Green's functions. We see each other later. Stay healthy.